And so now, as part of your lab, you will be implementing the Sensi algorithm. So I'll go over the overall structure of the algorithm and some key points for your understanding. But please note that there are some simplifications, and so I recommend you to refer to the step-by-step details in the lab and also the original paper. Now, the algorithm itself takes as an input a reference scan y of t minus 1, the current scan y of t, and then some initial guess of the roto transformation q0, which I will explain shortly. Given these inputs, the output of the algorithm is the transformation q, which is the converged solution representing the rotor transformation between the two scans at y, the two scans y of t minus 1 and yt. Now, at any given iteration of the algorithm t equal to k, we use the previous guess q of k to transform the coordinates of the current scan into the frame of the previous scan. And then for each point, we then find the closest line segment, which is the point-to-line correspondence search that we covered before. And then based off of these correspondences, we then update the transform in two steps, where we first formulate the point-to-line error objective, and then we find this next iteration of the transform q of k plus 1 that will minimize this objective. And we'll go into detail about this shortly. This algorithm will repeat until we converge to a particular solution. Now, in the remainder of this lecture, I will explain the details of this algorithm from the code's perspective, which you will need to implement in this lab. And so the main module that implements this algorithm is the scan processor and the scan match CPP file. In particular, you'll have to implement the handle laser scan function, which I'll explain next. The handle laser scan function is structured in the way that it uses the previous guess, q of k, to transform the coordinates of the current scan into the reference frame of the previous scan. This is indicated here in red in the code. Now, this transform q of k is a tuple t of k and theta k, where t of k is the translation in x and y, and theta k is the degree of rotation of the position. And so for the ith point, we define the roto translation operator r that and the translated point p of I of w, which is basically p of I that's been rotated by some theta value and translated by t of k. So p of I of w is the newly translated point within the reference frame of the previous scan. After this coordinate transform has occurred, the set of correspondences at iteration k is defined as c of k, where each element is some tuple that determines which line segment a point is closest to. Now, for this first part of the lab, we'll use a naive correspondence search, where you basically just do a exhaustive search of trying to find the closest line segment. But we will implement some improvements, which we'll cover next time, that will greatly make this correspondence match much more efficient. After the correspondences have been found, the transform is then updated in the update transform function. Now, to do this update, we first proceed by formulating the point-to-line metric objective shown here. Now, this may look very complicated, but in fact, we can understand this if we recall some basic vector geometry. So let's say that we're given the point pi of w and the line segment pj1 to pj2. If we want to be able to find the distance from the point to the line, we first have to we have to define what this distance is. And so in order to do this, we first define the vector A, which is the vector going between pj2, a point on the line segment, and piw. Next, the normal vector n of I is the vector that is perpendicular to this particular line segment. And the angle between these two vectors is theta. From vector geometry, we know that the inner product of n and a, or n transpose a, is the same as the transpose a of transpose of is the same as a transpose n, and by definition is the magnitude of a times the magnitude of n times cosine theta, the angle between them. Since the magnitude of the normal vector is 1, this ends up being a cosine theta. And so this inner product is exactly the distance from the point to the line that we desire to compute. So recalling the point to line metric objective here, for the ith point, we can see how this point is the translated point P of I of W. And this expression here is the same as our vector A, representing the vector between one point of the line segment and our transformed point. N of I is the normal vector for the line segment. And finally, this is the inner product which computes the distance from the transformed point to the line segment that is corresponding to that point. Thus, the objective is simply summing up all of these distances between the point of one set and the corresponding line segments. Now, given this objective, we then solve the optimization problem, which tries to minimize the objective function in order to obtain q of k plus 1, or the next best guess. And so more formally, the optimization problem minimizes over theta and t, which define this rotor transform q, in order to minimize the objective function j. Next, I'll go over briefly how the closed form solution for this problem is derived as it pertains to the implementation. But this portion may be a little bit difficult to understand on the first pass, and so I recommend reviewing the original paper for the full derivation. Now, in order to derive the solution, we first rewrite the objective by defining a few variables. First, we define pi of I to be p of ji, which is the corresponding point for the transform point. We define the state vector x to represent the transform q, where the components correspond to the translation in x and y, and also an equivalent expression for the angle theta using cosine and sine is obtained by setting the constraint x3 squared plus x4 squared is equal to 1. In addition, for each point pi, we define the matrix M of I as such, and also the matrix W, and similarly the matrix C of I. With some algebraic manipulation and using these definitions of the variables, we can rewrite the objective function as follows. I'll leave this derivation to the listener or student in order to as an exercise. Now, some of you who are familiar with convex optimization will recognize this as a quadratically constrained quadratic program. Now, I can't go into the details of convex optimization as an entire course can be dedicated to this topic alone, but I will provide some intuition behind how this problem is solved in order to obtain an optimal solution x in the general case. Now, imagine that our objective function is a convex function g of w, and we are searching over the domain of w. Directly finding the solution that minimizes this objective is often very difficult. And so instead, what we do is use an iterative process where we start from some initial guess w0, and approximate the objective function around this initial solution of W0, shown as the blue parabola that is kind of that is intersecting the objective function at that point, at the point W0. The point which minimizes this approximation is found, which is W1, and is used as the starting point for the next iteration. This continues until eventually the algorithm converges to the optimal solution, W star. Now, the reason why we like to use convex functions and formulate a convex optimization problem is that for convex optimization problems, once you converge to an objective, the solution is guaranteed to be the global solution. Now, unfortunately, a quadratically constrained quadratic program is not convex in the general sense. So there are specific cases where it is convex, but generally they are not. And in this case, and especially for our problem, it's not a convex problem. And so the only guarantee that we have is that we have reached some local minima in terms of the solution. However, all is not lost in that scan matching itself is an iterative algorithm that solves for the next best solution, and at every iteration, fortunately, we have this closed form solution that makes the algorithm much more efficient. And so I will now go into the derivation of this closed form solution. But as before, I'll focus on how to implement the solution in code. And so the detailed derivation of the solution can actually be found in the paper. Now, in order to find the solution to the optimization problem, which we derived before, we implement the computations in the update transform function. The first step is to define the M's, C, and W matrices for the objective function and the constraint. Note that we're using the C++ library eigen in order to define these matrices and the matrix observations. Now, by expanding out the expression of the objective function and regrouping according to the X, we can define the matrices M and G and rewrite the objective in terms of M, W, and G. Now, this is implemented in the sections of skeleton code indicated on the right, and this is part of the exercise that you will have to go through during the lab. Now, in order to find the solution X, we formulate what's called the Lagrangian. Now, intuitively, you can think of the Lagrangian as a way to express both the original problem and the constraints of this problem as a single problem, which can be solved in terms of the original variables and the Lagrangian variables lambda. Now, to solve this problem, we will first derive the gradient with respect to x and set it to be 0, as shown here. The solution to x is found as an expression of the known m, w, and g constants and the unknown variable lambda. Therefore, in order to find the solution x and compute it, we need to find lambda. And so the rest of the derivation is how to find this particular lambda. If we substitute x into the constraint and organize it into the constraint x transpose wx is equal to 1, we'll end up with the expression that you see here. And from this expression, we will first derive some expressions from for the submatrices A, B, and D for 2m plus 2 lambda w. This can be seen in the code, and your assignment will be to derive these expressions for A, B, and D based off of this definition. Now, there are some additional steps in this derivation. But basically, the matrix Q and its inverse Q is defined in terms of the matrix S and S of A, as shown here. And so, in this assignment, you have to define the matrix S and S of A using the A, B, and D submatrices that we found in the previous step. Now, once Q and Q inverse have been defined, as shown here, according to the values of A, B, and D, S, and S of A, after some additional steps of manipulation, the expression for lambda will become this polynomial expression in terms of lambda. And so if you look at this carefully, you'll see that each of these expressions indicated in red define a coefficient in the quartic polynomial and p lambda is squared. So with these coefficients, you can then use the provided greatest real root function in order to solve for lambda. And with this lambda value, the value of x can be computed, and subsequently the components of the transform can be extracted from x. So in summary, in this first part of the scan matching lab, we'll be focusing on implementing this update transform function. And during this part of the lab, we'll use a naive version of the get correspondence function that is provided for you. However, next time, we will cover some other tricks that will allow us to speed up the correspondence search process. Now, some key takeaways from today's lecture is that localization is an important component for autonomous systems, and scan matching is one particular approach to localization. Another kind of more general takeaway is that many problems related to robotics are formulated as an optimization problem. And as we've shown in our situation as well, many times these problems are non-convex. And so we'll deal with we'll cover how to deal with some of these non-convexities, non-convex optimization problems later on in the course. And next time, we'll cover the fast correspondence search, which is the second part of the innovations of the PLICP algorithm.